So let's talk about a very important chapter from physics, that is system of particles and rotational motion. This chapter is very important, and this chapter is including maximum number of questions in the question paper, and this chapter is thought to be very difficult also, but we'll try to revise each and everything. But whatever important points are there, that is must to be covered. So if we see the analysis of this chapter, system of particles and rotational motion, in 2009 three questions was there, and then in 2017 there were about three questions, and 2019 three questions, and 2020 two questions, and 2021 also so many questions were there. So now let's discuss this chapter important points, and we'll cover everything. This chapter is very important to revise. So in the NEET preparation, the most important thing is revision. Everyone studies the chapter in so much detail, but when it comes to examination, the overall chapters, the formulas are very important. So for this we need a short revision thing to revise each and everything. So I'm going to have and explain read and explain all the important points that is required. So let's start. System of particles and rotational motion. Center of mass. The center of mass of a system of particles is the point that moves as whole mass of the system is concentrated there and all external forces are applied there. So what is center of mass? What is center of mass? Let's discuss. The center of mass of a system of particles is the point that moves as the whole mass of the system is concentrated and all external forces are applied there. What is center of mass of a two particle system? What is center of mass of a two particle system? So in figure A, two particles of masses m1 and m2 separated by distance d and the origin of an axis coincide with the particle of mass m1. So what is given in the figure is m1 is the mass which is present exactly on the origin, at the origin itself. So the position of the center of mass COM of the two particle system is given by XCOM is equal to m2 by m1 plus m2 into d. m2 by m1 plus m2 into d. In figure B, in which the coordinate system has been shifted leftwards. So in figure B, in which the coordinate system has been shifted leftwards. So what happened? Now we have shifted the m1 away from the origin. Okay, the position of the center of mass is XCOM is equal to m1 x1 plus m2 x2 by m1 plus m2. Similarly, for y-axis and z-axis, ycom is equal to m1 y1 plus m2 y2 plus m2 y2 by m1 plus m2. zcom is m1 z1 plus m2 z2 by m1 plus m2. Now, center of mass of n particle system. For a system of n particles of masses m1, m2, m3 and so on mn, having the position vectors r1, r2 and so on rn respectively with respect to coordinate system, therefore the position of the center of mass of a system of n particles is given by a position vector. RCM is equal to m1 r1 plus m2 r2 plus so on mn rn by m1 plus m2 plus so on mn. So you can write like summation of n m1 r1 mi ri by total mass m. So where capital M is the total mass of the system. The coordinates of center of mass are given by XCOM is equal to the coordinates of the center of mass are given by XCOM is equal to summation of n mixi by capital M. Capital M is total mass of the system. YCOM is summation m1 mi by m. ZCOM is summation mizi by m. Center of mass of rigid body or continuous distribution of mass. The solid bodies contain so many particles, atoms, that we can treat as a continuous distribution of matter. The particles then become differential mass system dm. The sum become integrals and the coordinates of the center of mass are defined as Center of mass of rigid bodies or continuous distribution of mass. The solid bodies contain so many particles. Center of mass of rigid body for continuous distribution of mass. The solid bodies contain so many particles, atoms, that we can treat as a continuous distribution of matter. The particles then become differential mass elements dm. Some become integrals, and the coordinates of the center of mass are defined as xum is equal to 1 by m integration x dm. Yum is 1 by m integration y dm. Zum is 1 by m integration z dm, where m is mass of the body. The position of the center of mass of a system is independent of the choice of coordinate system. The position of the center of mass depends on the shape of the body and distribution of its mass. Hence, it may lie within or outside the material of the body. In symmetrical bodies in which the distribution of mass is homogeneous, the center of mass coincides with the center of system or geometrical center. The center of mass changes its position only under translatory motion but remains unchanged in rotatory motion. Center of mass of some well-known rigid bodies are given below. Center of mass of a uniform rectangular, square or circular plates lie at its center.